Hi, welcome back. We've been calculating the continuous time Fourier transform, and really honestly the CTFT is not really calculated by hand in practice. What we do is we calculate the CTFT for basic shapes and basic mathematical functions like square waves and sawtooth waves and these things. But then when we actually have an application, we relate the more complicated wave to these basic waveforms, and we find a relationship, and then we use properties of the continuous time Fourier transform to get the Fourier transform quickly using previous results. And so that's what we're going to do today, and in this video and in the next couple of videos. We did a similar thing for Fourier series and properties of Fourier series, so a lot of this is going to look very similar to that. Now, I will prove some of these properties at the beginning, but then going forward, it's not really a good use of our time to prove all these properties. So I'll give you the result after a while. So for linearity, we're going to say, suppose x of t has a Fourier transform x of j omega like this, and y of t has a Fourier transform y of j omega. Okay, and then we want to know what is the Fourier transform of some constant alpha times x plus a different constant beta times y. That's what we're trying to find. So let's do it. So I look to the analysis equation. This is minus infinity to infinity of the signal whose Fourier transform you're trying to find. So our signal is this linear combination of x and y, right? Then multiply that by e to the minus j omega t dt, and from properties of integrals, right, the integral of a sum is the sum of the integrals, and then I can bring out the constants, and so I have something like this, right? I've got that piece separately, and then I've got plus beta times this piece, e to the minus j omega t dt, and I look at this. Well, what is this thing? Well, this is alpha times, and that's exactly the analysis equation for x of t. So this is alpha times x j omega, right? Plus, and what is this? This is beta times, and then this is the analysis equation for y of t, plus beta times y of j omega. So we conclude that alpha x plus beta y has the Fourier transform, almost what you would expect, right? Alpha x plus beta y, capital. All right, so we get the same linear combination of the frequency components. That's the result. All right, so we'll apply that later on in an example, future video. Okay, the next property I want to look at is the time shift property. So again, we're going to suppose that x has Fourier transform capital X, and we want to know what is the Fourier transform of x shifted by some constant t0. Well, let me use the analysis equation. This is x of t minus t0 e to the minus j omega t dt, right? And then I'm going to change the variables. I'm going to say, so let me just write this down, change of variables. I'm going to let some variable tau equal t minus t0, and the idea is that I'm going to have x of one variable. That's what I want to be able to compare this to the analysis equation. So as t goes from minus infinity to infinity, tau also goes minus infinity to infinity. So I'm good there. Then this is x of tau, that's what I want, e to the minus j omega. Then if I solve this for tau, or for t, I get tau plus t0, right? And then dt is d tau. If I take a differential of both sides, this is just a constant, so it goes away. D tau equals dt. Okay, so now from properties of exponents and the integration, I can bring out e to the minus j omega t0 out of that integral. And then what am I left with? I've got the analysis equation then, right? Yes, we're calling it the t tau, but still, it doesn't matter what you call it. The fact is that I'm integrating over this tau. I've got e to the minus j omega tau, x of tau from minus infinity to infinity. So what is that? That's exactly the Fourier transform of x. And so we conclude then that, again, x delayed, or maybe not delayed, but advanced also, but shifted by t0 has the Fourier transform e to the minus j omega t0 times its original transform. So shifting in time does not change the magnitude of its Fourier transform, because the magnitude of e to the minus j omega t0 is just 1. The magnitude of that thing is 1. So shifting does not change the magnitude. Shifting only changes the phase components of the Fourier transform, and that's exactly what we expect when we talk about shifting a waveform in time. We're changing its phase, not its amplitude, not its magnitude. Right? Okay, so now for conjugation symmetry, we're going to again suppose that x of t has Fourier transform x of j omega. So this is one that I think we're going to forego the proof, and I just want to talk about the result and why the result is important. So if x has Fourier transform capital X, then it turns out that x is complex conjugate. So if we conjugated this signal, we would find that we would have a transform that would be the complex conjugate, but flipped as well. Okay, so that's the result. That's conjugation symmetry. And the consequences to this are what I wanted to discuss. Consequences. So just on this alone, actually, I should say suppose x is real. Okay, in that case, x of t equals its complex conjugate, right? If you take the complex conjugate, then you get back x. Complex conjugate of a real sequence or a real signal is itself. And so this implies that this is true, right? That x's Fourier transform must be equal to, if the left of is equal, then the right is equal as well. So now the consequences of this thing, then, if you suppose x of t is real, then that means x of j omega or let me back up, I guess. The real part. So remember that the Fourier transform has a real part, an imaginary part, or a magnitude and a phase. The real part is even. The imaginary part is odd. The magnitude is even. We've already seen these actually in some examples prior to this video. And the phase is odd. Now, if we further require that x of t, so I'll say suppose x of t is even, then it turns out that x of j omega, its Fourier transform, is also even. And if we instead suppose x of t is odd, then x of j omega is also odd. So remember why these symmetries are so important. They are important because we have to have programs and we have to have circuitry that calculate these Fourier transforms for us. So if you can exploit some symmetry, then if you have a continuous time system, then you only need approximately half the hardware that you would need otherwise. And if you have a discrete time system, which we'll talk about later, then you only need half roughly the computational time and the computational resources, memory, to process those Fourier transforms. That's why those are important. Okay, so we're going to cover some more properties in the subsequent videos. I will see you there.